Right. So the screen is visible, right?
Yes, sir.
Great. Okay. So I think last time we were doing again fluid mechanics, and we did a lot of problems from pipe flows and frictional losses in pipes. And I guess at the end we had left off with this homework problem. And so today we will first start off with this. And once we solve this one, we will go on to a topic which is a little relevant in terms of fluid dynamics when you are doing this engineering services exam. But I don't know if there will be a lot of questions from GATE from that topic. So this is fluid statics and stability and the forces that hydrostatic forces that act upon a body when it is immersed in a fluid. So we will see that later, but let's start with this question from GATE 2020. And did anyone try this, by the way? So I had given some
Sir,
hints last time. Yeah, yeah.
yes, sir. Um, if this kind of problem we have to face and get, then that's the time consuming. What I have faced during
Yeah,
solving that
so
problem.
I think you are right. So in this, you
It
will
took,
need to do some integration, and that will take some
yeah,
time. So,
yeah.
yeah, but there will be a few questions like this, which I mean you will have to
It took
spend
almost
some more.
15 or 20 minutes to solve that.
Uh, no, Abhijit, I think 15 minutes is too much. If you are spending
Yeah,
15 minutes on one question, better to
yeah, that's why.
yeah
Yeah.
skip it, and maybe if there is time, come back to it at the end, because 15 minute is like too much for one single question.
Hmm.
Mm. Yeah, but did you get the value of n by any chance, or anyone else?
Yeah,
So what did you get?
yeah. Rho c cube pi by 8 d to
Uh,
the power 8.
no, 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 no. Yeah, so you just need to put n here. N is like the exponent of t.
Okay.
Yeah, yeah. So what's the power of diameter you are getting at the end?
Diameter, actually, I calculated kinetic energy.
I think you mean kinetic energy, right?
Yes, sir.
Yeah, okay. Kinetic energy will be a function of diameter, I think, capital D.
Hmm.
And so basically, they are saying that Ke is proportional to d raised to power some n, and this n is what we need to find. So were you able to get Ke, sorry, not Ke dot basically. So this is rate of kinetic energy and not just kinetic energy, because we
Hmm.
are talking about a fluid and not a solid. So did you get some expression which is proportional to t, or
So
anyone
rho c
else?
cube, by using a minus b whole cube formula, I
Yeah,
got
yeah.
rho by c cube r to the power 6 integration limit with 0 to r,
You have
1
to,
minus,
yeah, you have to integrate actually.
yes, 1
Hmm.
minus r small r square by capital R square
Yeah.
cube r integration of dr. Yeah, sorry, differentiation of dr. R dr.
Yeah. Anyone else? Anyone else tried this one?
Sir, are these videos are uploaded on YouTube?
Mm, I
Uh,
don't think so.
Hello?
Yeah, the videos might not be uploaded on YouTube, but we have all the videos saved on a Google Drive, which I think at the end someone can share the link of the Google Drive. Uh, but okay, for the timing, let's focus on the question. We can figure these logistics out at the end. So anyone else? Anyone else tried this?
So is it seven?
Ashwin, did you say seven?
Yes, sir.
Okay. Okay, let's see. Yeah, I think it might be eight, but yeah, we'll do the calculations. Did anyone get 8 by any chance?
Yes, sir. It's 8.
Yeah, yeah, okay. Yeah, so it should be 8, and I guess we can try to see it how it comes. But so this is ideally this is all you need to know. So the rate of kinetic energy is just given by half m dot v square, where m dot is the mass flow rate. So here m dot is the mass flow rate, and this m dot can be written as density times q, where q is the discharge, or you can also call it as volumetric flow rate. Right, so the units will be meter cube per second. Yeah, but anyway, so I think in the last class we had already seen how to proceed with this, so I will not go into the details. I'll just write that Ke dot will be equal to half m dot v square, and we can say that m dot is rho times q, where q is given by velocity times dA, some elemental area dA, and that dA, since this is a circular pipe, can be written as 2 pi r dr in terms of elemental radius. So then you can just write this as half rho times v times 2 pi r dr, and then there is a v square which comes from here. Now you can club the v's together, so this will be half rho 2 pi r v cube dr. And now we have been given this expression for v. This is like a parabolic profile. So v is given as minus of c r square minus d square over 4. So you can substitute this here. So you will notice that everything will come in terms of the radial distance. So this variable radial distance, which goes from 0 to capital R, or capital D by 2, since the diameter is given here. So then you can say that this is half rho 2 pi. Instead of v cube, we can substitute this. So this will be c cube minus of that, since there's a minus in front. And then there will be r square minus d square over 4 whole cube. And then you will have one more r here, which is this one, times dr. So now this is just a matter of doing integration now. So I guess we can cancel this 2 and 2 out. And all of this can be considered as a bigger constant, because c is a constant and rho is a constant. And this minus also we can absorb with this. Let's say this is some capital K. And this now we can use the formula of a minus b whole cube. So that will be equal to a cube. So r square to the cube of r square will be r raised to the power 6 minus, so this will be your d square over 4 raised to the power 3. So this again becomes d raised to the power 6 over 64. So by the way, what is the formula for a minus b whole cube? Can someone tell me that?
Yeah, a cube minus b cube minus 3ab into a minus b.
A minus b. Right. So we are using this formula here. So you have this a cube minus b cube. Now you will have 3 times a, which is r square, b, which is d square over 4, and then you have this a minus b, which is again r square minus d square over 4. Now outside this you have one more r, and be careful, do not forget this, because if you forget this, then you will get a incorrect exponent in the end. But anyway, we can now take k again outside, and multiply everything inside. So this r can come inside, and then it will be r is to the power 7 minus d6 r over 64 minus, so I'll multiply this within inside the bracket, and then also multiply it with r. So this is 3r square times r square, which is r is to the power 4, and one more r from outside. So this is 3r power 5 d square over 4 minus, now this will be multiplied with this, so this is 16 in the denominator, and this 3r square will be multiplied with one more r here, so this is 3r cube, and d square times d square will be d raised to the power 4, and since this is minus times minus, this will be a plus here, dr. Now you just integrate this, and while integrating you just need to integrate from 0, because r goes from 0 and it will go on until d by 2, right? So then we integrate this whole expression from r going from 0 to d by 2, and I'll just write down the results. So this will be r raised to the power 8 over, yeah, 8, and this is d raised to the power 6 r square over 128. Again you will have 1 r raised to the power 6 here, so this is 3 times r raised to the power 6 over 6 into 4 is 24 t square, plus this will be 3 times r raised to the power 4, 16 times 4 is 64 t power 4, and in the end you just substitute the limits. So these limits go from 0 until d by 2. So now after this I don't think you need to solve it any further, because you can clearly see if you substitute for d, you will get that k will be proportional to d raised to the power 8, because all of these here you can see, you can substitute here, so this will become d some d raised to the power 8, and this is d6 times d square again, so d raised to the power 8, and then since they are only asking you for the exponent, not the whole expression, so you can just simply say that this will be, that k dot will be proportional to d raised to the power 8.
Sir,
Yeah.
sir, actually, while splitting this row Q into row V dot dA was a bit difficult, sir, because initially I thought it'd be half row Q V square. Like whether a Q is constant or A is constant, that was difficult to decide.
uh no, see, q is a function of a, right? So if a is not constant, then q cannot be a constant.
So when we have flow through pipes, the Q is not constant, sir, at every section.
No, it at every section, if you see here at AB and at CD, let's say this is AB and this is CD, it will be the same. But there is this small section. So here you are cutting this DR, right? So
Yes.
here it won't mean, it will vary with the radius, because the area changes with the radius. That's all. So let's say you have a small pipe and then you have a larger pipe. So both of them will have a different flow rate, right? Because I mean, the radius are different ideally, even if the velocity is same. But again, here we have been given that velocity is itself a function of radius. Then it becomes easier to make everything as a function of radius. So basically, what we have done here is kinetic energy has been computed as a function of radius, and when you integrate it over r, so throughout the whole radius, then you get it as some function of this capital D or capital R, which is like the overall radius of the pipe.
Yes.
Yeah. So yeah, that's the case. But yeah, I think
So
that is the key part. Here you need to just know how to write kinetic energy rate in terms of the flow rate, and then See, as I said, you don't even need to do the whole integration basically. You just need to put it in the final form and then smartly see what they have asked in the question. Since they are only bothered about the exponent of d, so it makes sense just to yeah, put the limit here and then just write down the answer as 8. Yeah, Vijit, you had a question.
Yeah, if we face as such questions middle of the
Yeah. Mm, can you
right.
repeat, Avishit? I can't hear you.
Uh, Actually, should we leave
No, no, no. I don't think you should leave
during
this. See, Avijit, I think you were spending too much time doing this integration and getting to a final expression. So that is in a
yes,
way
yes,
time waste, right? Because they have not
mm,
asked you for the full blown expression of ke as a function of d. They just want you to put down the exponent, and for that, I don't think you will be needing 15 minutes to solve this integration. This is just a simple integration of polynomial function. So means you just have to raise the power by
polynomial.
1 and divide it
Yeah.
by that same number.
Mm, mm,
So I mean, okay, ideally, if you think that you are taking longer than you should skip the question and come back to it at the end. But
mm.
I don't think this question, requires a lot of time once you know what they have asked. So always carefully read the question first and then go on to solve the problem.
Okay, sir.
Yeah,
Thank you.
yeah. So let's now. Okay, this is I think clear now. So we can move on to the next topic. And today, I guess we will be doing a bit more theory and less number of questions because I think in the last class also someone had asked this question of center of pressure. So I wanted to discuss this topic of hydrostatic forces on submerged plane surfaces. So we will only be dealing with plane surfaces here. And I have not seen a question come from this topic in the last 10-15 years at least. But since someone had raised this doubt, so it's better that we discuss this the whole class. So the setup is very simple. You have some kind of a body, and this is a plane surface right now, which is submerged in some fluid. Let's say this is your fluid, so this pink color. And this schematic, by the way, I have taken from again the same book, Fluid Mechanics Fundamentals and Application by Sengel. A very nice book. And if you want to know more, you want to go in depth with this topic or any other topic, you can just go through that book. But we will see if this is the configuration where, so how does the, so you basically you will have some kind of hydrostatic pressure which varies with depth. We have already seen that P is rho GH. So this is our hydrostatic pressure. Yeah, the hydrostatic pressure. And we know that this hydrostatic pressure, so whenever you have pressure, this pressure can impose some force on the body, and that is what we are after here. So this hydrostatic force comes from the hydrostatic pressure, and we know that this hydrostatic pressure varies with depth. So your force will vary with depth, and here if you see this plate, you can see that these vector lines are basically your force, and this magnitude is represented by this length of the vector lines, and you can see that the magnitude is increasing as we are going down in z, or basically down in depth. That is because pressure will linearly increase when you go down in depth. Now we have two objectives here. First one is to find like a net resultant force on this submerged body or submerged surface. So first is to find the
Hello,
net
sir.
force. Yeah.
Hello.
Hello. Hello. Can you hear me? Hello. Yeah. You can hear me right now?
Yes.
Yeah. Okay. So I was saying that I don't know how much you guys heard, but here we are trying to see how hydrostatic forces are applied on a body which is submerged in a fluid. And we already know that the hydrostatic pressure varies linearly with height. So as you go down in depth, the hydrostatic pressure increases, and given by this expression rho times g times h. And also here, if you see in this illustration which I have taken from the book Senkel, Fluid Mechanics Fundamentals and Application. Here you have this plane surface which experiences force because of hydrostatic pressure, and this force is the magnitude of this force is represented by these vector lines. And you can notice that as you go down in depth, these vector lines are increasing. Basically the magnitude increases because the pressure is increasing. So now we have two objectives here. First one is to calculate the net force which acts on the surface. And when I say net force, because this body is in static equilibrium, so that will be the net hydrostatic force. So you will have some net hydrostatic force which acts on the surface. The second objective is to find out at what point this force acts. Right. So we will first find out the net force, and then we will find at what point this force acts basically. And uh, this is that point, and this point is called the center of pressure. So center of pressure is just the point on which the net hydrostatic force on a body which is submerged in a fluid acts. Right. So I'll do this short derivation. So this is not very lengthy. Basically, what you need to do is just take your pressure. So we are assuming here there is some pressure at the surface which is P naught. P naught you can think of it as P atmospheric, so atmospheric pressure. So now let's say I have some elemental area dA, and this is the projection of that body, and this dA is at some height y along this direction. So this is your y and this is your x. Sorry, this is your z, this is your y. So now we are saying that force is given by pressure times the area, and this force will be the atmospheric pressure P naught plus rho times g times some height h corresponding to this y. So when you are at this point y, there is this height h, and you can use the hydrostatic law to say that this will be rho times g times h times dA. Now this h you can again write in terms of y, which is along the plane. So then you can just say that this is P naught plus rho times g times y sine theta times dA. Now, in order to calculate the net force, you will have to integrate this elemental dA throughout the whole area of the body. So then this becomes P naught times A, or let me just write dA and then we can do it in the next step. So this will be P naught times dA plus rho g sine theta y dA. Now this P naught times dA, you can simply write P naught times A, where A is the total area of the body. So plane surface of area A, this is the body. And this rho g sine theta remains as it is. Now this y times dA, if you remember your engineering mechanics classes, you can write this as the centroid of the body. So there is this expression, let me just write it here and maybe in a different color. So yeah, let's take blue. So we have this property that the centroid of any body is simply the average of this first moment, and this is what we'll use here. So we have y times dA, so you can write this y times dA as yc. Yeah, so this can be written as yc times A, or you can write this as P naught plus rho g sine theta yc times A. Now this yc is nothing but just the centroid of the plate or the surface, and this centroid will be at the center. So this C gives you the centroid, and so you can also club this yc sine theta and call it some hc, and this is that expression which is written here. So this is called as the pressure at the centroid PC, and this is your area A, and this PC is given as just P naught plus rho g HC, where HC is YC times sine theta, and where YC is the centroid of the body. So this will be your net force, net hydrostatic force. Now this net hydrostatic force does not act on the centroid, which is intuitively easy to see. Let me just go down to this different schematic, and you can see that since the pressure is varying linearly, so this will not act at the centroid, but it will act somewhere to the left of it, because you can think of it as some kind of mass uniformly varying mass distribution. And since the mass distribution is higher on the left edge, so this whole net force should be acting on the left edge when looking from the front. So that's what happens. So this center of pressure is at a different point as compared to your centroid. So this is your centroid C, and this is your center of pressure P. Now in order to calculate the center of pressure, you will need to do a moment balance. So you can say that Fr times y of P, where y of P is your, so P is your center of pressure and y of P is this distance. Yeah, actually it is written there only. So y of P is distance from some origin to the center of pressure. So this is distance from O to P. Now Fr times Yp, so this is the net hydrostatic force times Yp, will just again be the integration of Y times PdA. So this is similar to the derivation last time, but here we have this moment basically, and then again you can write P as similarly as last time as P naught plus rho g y sine theta. So now this is using the hydrostatic law times dA, and then you have to integrate this. So this becomes P naught times y dA plus rho g sine theta y square dA. Again, from your engineering mechanics class, you should know that this, so this we already know will be some yc times a, and this y square dA is called as the second moment of area, or the moment of inertia, which you can write as y-axis, and this is about this point O. So this x goes inside or outside the plane, the x-axis, and your moment of inertia is about this point O. But usually we know some typical moment of inertia about the centroid of the body. So then you can actually use the parallaxis theorem. This again is from engineering mechanics, and you can say that the moment of inertia of the body around this point O origin will be nothing but the moment of inertia around the centroid, about the centroid, sorry. So C plus the distance square. So this is yc square times the area of the body. So this is using the parallaxis theorem. Yeah, the parallaxis theorem. And then once you do that and substitute it here, I guess you can do the calculation by yourself. Finally, you will reach this formula. So y of p will be equal to y of c. So basically the distance till the centroid C plus the moment of inertia around the centroid divided by yc plus p naught over rho g sine theta times the area. So this is basically just doing, substituting fr from the previous slide and dividing it by fr, and then also substituting ixx moment of inertia around O to be equal to using the parallaxis theorem, moment of inertia around the centroid plus yc square times a. So if you do that, you will get to this expression, and this is your expression for finding the distance from the origin to the center of pressure. Now you can easily see that this will always be greater than or equal to yc. So this will be equal to yc when this is in a flatter configuration. When the body is flat, then p and c will coincide. But in any case, yp will always be greater than yc or equal to yc. And yeah, I think we won't have time to get into this example, or maybe at least for FR I can do. So let's say now we are in a situation where we have this kind of geometry. So this is your flat rectangular plate of dimension b times a times b. So this is a rectangle with dimension a cross b, and this is inclined at an angle theta. So now this FR will be simply P naught, which will be now atmospheric pressure, plus rho times G times HC, and then area is nothing but A times B. Now this HC we already see is YC sine of theta, and this YC will be nothing but let's say this is your centroid. So this will be basically B by 2. And then this plate is a distance s below the origin. So you can simply say that yc will be s plus p by 2. Then you can just substitute and say that the net pressure Fr will be equal to P naught plus rho G S plus P by 2 sine of theta times AB, where AB is the area of the tilted rectangle. So, I mean, along this breadth P, you will have some length L. And then similarly, you can find YP. Maybe you can do this as in homework. Just find the YP of this. I will tell you what the moment of inertia of a rectangle is around its centroid C, which is equal to A times B cube over 12. So that's the only information you need, and then you can simply calculate this point P. So this will be your C and this will be your P. So I think we have spent enough time on this, but yeah, so this is one concept that I wanted to discuss today. Please try to find YP when you have time. We will move on to the next thing if no one has any doubts on this. Okay, let me just go to this now. So this is about the stability of immersed bodies. And so here you will have two cases now. Now, either the body is floating like a boat or it is immersed like a submarine. Okay, so this is a case of, let's say, we'll just write example, a submarine. And we are trying to find what happens when we slightly tilt this body, which is immersed. So you can have three kind of conditions here. First one, it can be stable. Second is when it can be neutrally stable. So being neutrally stable means, let's say I displace this circular ball slightly up or slightly down, then it will stay there. So we can probably make an analogy with some kind of a ball inside some kind of a potential well, or just a well, let's say. So this ball B is in a stable configuration right now, because if you slightly move it to the right, it will revert back to its original location B. But if it is on some kind of a hilltop, so if you slightly push it to the left or to the right, then it will keep on going down. So this is an unstable condition. And then can have one condition where this well is flat. So if you slightly push it to the right, this ball B will be here after some point of time. So this is a neutral condition. So these are the three things you can have. And when it is immersed in a fluid, then only thing you need to check about is whether the center of buoyancy given by this B is higher or lower than the center of gravity, or above or below the center of gravity. So let's look at this first case where it is stable. So the spoiler here is, whenever G is below B, you will have a stable configuration. Whereas whenever G is above B, you will have an unstable condition. So here, if we see the first case, since this ball is bottom heavy, so what happens is its center of gravity shifts little down, but its center of buoyancy, which only depends upon its volume and not its weight, will be at the center. So now in this case, let's say you have this kind of configuration, and then so this is your center line, and you slightly tilt it towards the right. So let's say I slightly tilt it towards the right, then the center line will replace. Now you already know that B is somewhere here and this is your G. So G will be below B in this condition because this is a bottom heavy object and G is down. Now this weight will act downwards, but since you have displaced this B, so you have a condition of generating moment which will be in the opposite sense to the perturbation that you have generated. So this G will be like this, whereas this B will be like this. Oh, sorry, not here, but in this half. So you see that this generates an anti-clockwise moment, which will actually try to tilt it back towards its original position. And in that way, you have a stable configuration when B is above G. So you have this stable condition. And by the way, this is only applicable for immersed bodies. We will move on to the floating bodies in the next slide. But you can reverse the situation now. And when you have again a top heavy configuration, then this G is on the top and you again slightly tilt the body. So then you have slightly tilted the body like this. Now what will happen is this B will come in this direction. So just so G again acts downwards. So this is your weight. Let me just write it here as well. Weight and buoyancy. And now you will have a clockwise movement instead of a counterclockwise movement. So this will enhance the tipping. So you will have buoyancy on the left side now. So this will actually generate a clockwise moment again. And then what happens is you will have another moment which helps it to somehow overturn, and then the condition is unstable. So when B is below G, you have unstable condition. And so when they design these submarines, they make sure that the design is such that it is bottom heavy. So basically all the engines and the passenger seats will be at the bottom of the submarine, so that this becomes bottom heavy and the submarine floats. So this is one and this is three. Yeah, so this is for immersed body, but when we go on to floating bodies, this is a little bit more complicated. So the first condition is whenever B is above G, then you already know that it will be stable. But here, even when G is above B, you can have condition where it is stable, and this is represented by uh, this configuration B. So here you can see that, okay, this is a floating body first of all. So some part of it is above the water surface, whereas some is below it. And again, you will have center of buoyancy acting somewhere. So given by this dot B, whereas the center of gravity is G. Now here in this case, the key player is this M, which is called as the metacenter. And this metacenter is nothing but the point where the axis of the body intersects with the center of buoyancy. So this is your center of buoyancy line. So this will always be vertical because it only depends upon the volume of fluid displaced. Okay. Whereas your gravity line depends upon the axis of the body. Since the axis of the body is tilted, this gravity line axis tilts, and wherever this axis line meets the center of buoyancy line, you get the metacentric point, and this distance mg or gm is called as the metacentric height. So this is some metacentric height. So you can do the same kind of analysis here, and say that if you have tilted this body like this, now since the metacenter is above uh, G and B, so it's not in between G and B basically, you will have a restoring force. So there will be this couple which will try to restore this body, whereas when this metacenter is below G, and then you have turned this body like this, so these two forces will again generate a couple which will enhance this turn, and basically flip over the whole floating object, and then this is an unstable condition. So I guess in the end the key point to remember is, for a floating body, when m is above g, you have a stable condition, whereas when m is below g, you have an unstable condition. So from all this discussion, that's all you need to know. And I think I've seen two three
Sir,
questions. Yeah, Vijay.
could we assume that for the A portion, the M would be zero, metacentric height would be zero,
Yeah. For A, the metacentric height is zero indeed, because see the line of
and for B, what it would be like, not zero, but would
positive
it
positive
be,
for
yeah.
okay. So I mean G. So this corresponds to GM being greater than zero, and this corresponds to GM being less than zero. So when the metacentric height is positive, greater than zero, you have a stable condition, whereas when the metacentric height is less than zero, you have an unstable condition. So maybe they can ask you in this way also. But I've seen like 3 4 questions just uh, asking you if asking you what kind of conditions are stable if m is below g, sorry, m is below g, b is below g, and all those things. So we'll see I guess one or two of these here, and I want you guys to answer this. So this is from gate 2020 set 2. So which of the following condition is used to determine the stable equilibrium of all partially submerged floating bodies? So you have to be careful and see that this is for floating bodies, and the 4 options are: center of buoyancy must be above the center of gravity, B is center of buoyancy must be below the center of
C,
gravity,
sir. C.
C is meta center must be higher level than center of gravity, yes, and I guess D is meta center must be at a lower level than center of gravity. So I think Abhijit is right, and we just saw this is the correct option. So I hope everyone was able to answer this immediately, because just we just saw this in the last step.
Sir, first two options are related to submerged bodies, isn't it?
Yes, yeah. So it will also be applicable for your what do you call it? These floating bodies, but floating bodies has this special condition where even when the center of buoyancy, so for submerged body or immersed bodies, you just need to know if B is above G. But for semi-submerged bodies or floating bodies, even when B is below G, such as in this condition, you can have stability arising when the metacenter is above G. So yeah, you are right. So these two will only work when the body is submerged or immersed, basically, because it has to be submerged fully. Okay. So this was easy, I think. And then there was one more same question which came in GATE of 2017. So, I mean, you might get, if you're lucky, a simple question asking you to mm, take the right stability condition for either a floating or a submerged body this year again. But let's see. This is from GATE 2016 now. For a floating body, buoyant force acts at the centroid of the floating body, center of the gravity of the body, centroid of the fluid vertically below the body, and the centroid of the fluid displaced. So this is also something you should be able to answer. So
So seems like A and B.
D.
yeah, I think this has to be D, because see, whenever you have the concept of buoyant force or buoyancy force, it will always be related to the fluid displaced by the body. So I think let's just see this. Maybe for an immersed body, you have this big block of body B, which is immersed in this fluid. Now, this will only be related to the fluid that has been displaced by this body B. So it has to act on the centroid of the displaced fluid. Right, so buoyancy force will
So then
always, yeah.
what's the problem with A centered of the floating body? It
See,
might
this is
also be
immersed body,
applicable,
right?
right?
So when you have a floating body, let's say like this, you will
Hmm.
have different centroids actually.
Ha, ha, ha,
So
ha.
here only this volume, okay, maybe I can draw a diagram which is better. So this is your beaker, let's say, and this is your water. All of this is water, and someone is joining now. And then you have this rectangular block. So let's say this is L by 2 and this is also L by 2. So you know the centroid is here, but the volume of fluid that it displaces will be just this much. So its center of buoyancy will be somewhere here. So this will be C, whereas this will be B. So only the volume of fluid that is displaced will give you the center of buoyancy. So this makes sense now, Vijay?
Hmm, hmm, hmm.
Yeah, yeah. Uh, okay, maybe we can do one more problem here. So this you guys should try. I'll leave this as homework again, but we can just go through the question. So this is a spherical balloon with a diameter 10 meter is shown in the figure below, is used for advertisements. The balloon is filled with helium and they have given you the gas constant of helium at ambient conditions of 15 degrees Celsius and 100 kilopascals. Assuming no disturbances due to wind, the maximum allowable weight in newtons of balloon material and rope required to avoid the fall of balloon, and then they have also given you the gas constant of air is. So I think you guys will be able to answer this. This is again from buoyancy. So does anybody want to tell me how you will proceed with this?
Equating buoyancy force to weight.
Mm, yeah. So I mean, so
Finding
basically,
density by real ideal gas equations.
yeah. Basically,
Yes,
first,
PV equal to MRT. Yeah.
yeah, P is equal to rho RT, ideally.
I mean MRT,
Yeah, yeah,
and
yeah, yeah, yeah.
then
It will
yeah.
little convert to yeah. So all of you are right. So first you need to do P is equal to rho RT, get rho from here, and then this rho will give you the weight of so from rho you can calculate the weight of the helium balloon, also the weight of the air which it will displace, knowing that it is a spherical balloon. So the
Sir,
diameter,
weight or density, sir?
no, from density you will have to eventually go to weight, right? Because
Okay.
density is mass over volume, right? And then you get mass and then you get volume, sorry, weight, just by multiplying it with g. And then in the end, you need to find the difference between the weight and the buoyancy force. So that is like the extra weight that you can put so that still the balloon does not fall, because as soon as the weight becomes higher than the buoyancy force, the balloon will drop down. So you just need to find out the maximum.
Differentiate between the
Uh,
this
yeah,
two force,
yeah, exactly. Difference between,
balloon and the air.
yeah, difference between the total weight and the buoyancy force will give you the maximum allowable weight that you can carry with this balloon.
Sir, is the answer 541 kg?
No, I think so. Here you have to answer in Newton. So, I mean,
Wait, yeah.
yeah. So you'll have to give the answer in newtons, and I think the answer is 5303 or something like that. So, I,
Yes, sir, I'm getting 5314.
14, yeah, something like that. 5314 newtons. So, please mind the units in which they are asking you the final answer. So here they want it in newtons, so you'll have to eventually multiply it with g and then get the weight.
Sir,
Yeah.
so can you please briefly solve it like just a method?
Yeah. So okay. Ashwin, why don't I solve it in next class? You guys can try it. I'll just tell you that rho is P over RT. From this, you will get a rho for helium and you'll get a rho for air. Okay. And then you know that the buoyancy force is nothing but the volume of displaced air times rho times g, right? So rho will be of air because air is your actual fluid air. So everything is in air. So this will give you the buoyancy force, and the weight of the balloon will simply be the density of helium balloon times the volume of the helium balloon, which is the spherical balloon simply. So, and this is G. And then the,
Same rate.
yeah, FP minus WB will be the maximum allowable weight that you can, let's say this is your F net force, which you can carry without the balloon falling. So, Ashwin, I think this can be done now, right? We can discuss this next class also if you want, not a problem.
Sure.
Yeah,
Okay.
yeah. So I
Can we
guess
get the drive links for the previous session?
uh, can you repeat? I can't hear you, please.
Sir, can we get the drive link for the previous section classes?
Okay. I think Priyanka, can you please share the link if you have it, or if not, I can also like pull it up, but it will take me some 2-3 minutes. Ask. Yeah. Anyone?
Yes.
Yeah. Do you have any doubts?
No, sir.
Okay. Okay. Good.
Thank you, sir.
Yeah. Yeah. I don't see anyone having any doubts. So just like last time, I will remind. Yeah, Krish, you have something to say?
Sir,
Yeah.
hello.
Yeah.
Sir, metacentric height varies from battleship and passenger ship. Why, sir? Changes to.
Wait. What did you mean? What were you saying? I can't understand you. Krish, can you repeat?
Sir, metacentric height, sir. Metacentric height.
Yeah, mid-centric height. Yes. What about it?
Changes to passenger ship and battleship, sir.
Oh, yeah, I have no idea about this, but I think there might be, yeah, I mean, so the larger is the metacentric height, more stable is the ship. So there will be differences between a passenger boat and what was the second one? Battleship. Uh, but I have no idea how big of a difference it is or not. I guess you will need a more stable battleship because you don't want it to sink when you are, I mean, fighting with the enemy, right? But I can't tell you how big of a difference it is between these two. Yeah, it's an interesting question though. Yeah. So I was just saying that if you guys